Yes, class. Assalamu alaikum. Am I audible?
Walaikum salam, teacher. Yes, you're audible.
Okay, so Khalid, Memuna, Salman, Sana. I think Salman has to go somewhere. I'll be back, ma'am. All right. So Heinz principle we had started. These are the basic things that will come from Heinz principle. And these are confirmatory that definitely these part will come. Walaikum assalam, Sana. So class, Heinz principle basically said what? Heinz principle said that the secondary wavelets are because of the fresh sources or disturbances. Yes. So each point on a wavefront acts as a fresh source of new disturbance. That new disturbance is known as secondary wave or wavelet. The secondary wavelets spread out in all the directions with the speed of light in a given medium. New wavefront at any later time instant is given by forward envelope. So this way, this is the forward propulsion of wave that is given by Heinz principle. So I gave you assignment. I think did you all do that? Please do that assignment. It is just based on Heinz principle. Heinz principle also what? Simply this V is equal to speed into frequency, all these basic formulas. Just try the assignment. Because all the students are not submitting the assignment, we are not even able to discuss it. Otherwise, initially we used to discuss the assignment along with the test papers. No, right now only few students, very few students are submitting. Salman is submitting on the portal. Khalid submits regularly. So do keep on submitting your assignment. If somehow you're not able to access the assignment, please let me know. If it is not uploaded or some error is there, then I'll contact and let you know. Because otherwise I don't have any update of whether assignment has actually reached to you or not. Now, 2 points were left, refraction and reflection based upon Heinz theory. This comes in your theory questions. Simple theory questions, this is asked to you. Reflection based upon Heinz principle. So see, reflection based upon Heinz principle, you have to prove it. Just theoretical questions come from here. You don't have to do any numerical from this. So this is a mirror. Exactly like this. You see, Heinz principle is straightforward. Whatever I have written it in the notes, no, whatever you have copied, it will exactly be the same for you. Same thing, same question, everything will be the same in your exam that will be asked. So just revise it as it is. Heinz principle is a very short part. Usually questions from interference and diffraction only come. But if it comes, it will be straightforward. So see, this is a mirror. Let's say M1 mirror, M1, M2. This is a mirror. Incident wavefront. This is the incident wavefront. This is the incident wavefront. Fine. Let's say this is A point. Now see what will happen. Reflection will occur. Fine. This is incident wavefront. Let's say incident, you have incident ray also. Incident ray will also be there, no? And how do you write incident ray? Incident rays are always drawn perpendicular to the wavefront. Remember when we did all these? Here, how did we write? Rays are perpendicular to the source. If this is the source, this is the wavefront, then these are the rays that I used to draw, no? Like this. So rays are always perpendicular. Incident ray will be perpendicular to this. This is incident ray. All right, this is incident ray, this is incident wavefront. Fine, so angle that the wavefront will form with the mirror, this will be angle of incidence. Now, incident ray on mirror, what will happen if an incident ray strikes on a plane mirror? It gets reflected. So here will be the reflected ray. This is exactly the same procedure which you have to remember. This is the reflected ray. This is the reflected ray. So if you see, the wavefront will be formed over here. That's why no reflected ray is here. It means the wavefront is formed. So for A point, I'm drawing this wavefront here. And this is B point. So the wavefront will be formed somewhere here because the distance is larger. So the wavefront will be formed at a larger distance. This is shorter, so this is formed. So for point A and some point B, I have drawn the two wavefronts. Now what we'll do? Let's connect the forward envelope. This is Heinz principle. Just this is the part where your Heinz principle is utilized. This becomes what? This is the reflected wavefront. Reflected wavefront. Even if incident ray falls on this point directly. Now see what will happen. Incident ray will fall at this point as well. The incident ray will fall at this point as well. This was one point that I had taken for this. Now incident ray will fall at this point. Now what will happen? Again here reflection will occur. This will again be the reflected ray. Again this will form here forward envelope. Wavefront will be there. Like this, it will keep on propagating, and that is what we have studied in Heinz principle, that how the propulsion occurs. The initial primary wavefront has the point, and these sources become the fresh sources for the new secondary wavelets. These are the secondary wavelets. These secondary wavefronts or wavelets, their forward envelope forms the new wavelength. Now this new wavefront, now this will act as a source of the new wavefront, and this way it will keep on propagating. This is what we had already studied for it. And yes, class, one more thing. This will become angle of reflection. This is the reflected wavefront. Oh, this was the incident wavefront. So this angle R, this becomes angle of reflection. All right, I think I've mentioned all the points. Also, one more thing, class. Speed into time is this distance that is covered by the reflected ray. For the distance, now I'm writing it as speed into time. So for all the rays, it becomes speed into time. Wherever speed of light is required, you will write ray of light speed, that is 3 into 10 to the power 8. Let's name this also. Some B dash, this point as A dash. A, B, A dash, B. So this, no, A dash, this is basically what? A dash, this is equal to B dash. This point, no, this point B dash. B dash, this is this is totally equal to B dash. In practical and through experiment, this has been found that A dash, this line and this line, both of this new incident wavefront and the reflected ray, both are equal. And equal to what? Because both are VT. That's why they are equal. All right, that's why they are equal. Now see, if you look over, no, let's see certain triangles for the derivation of this. Let's see certain triangles. If you look at this triangle, A dash, look at this triangle. Triangle A dash, And have a look at this triangle B, B dash A. B, B dash, A dash. This triangle and this triangle. And triangle B, B dash, A dash. So both these sides are equal, A dash, B dash, right? And look at this angle A, no, this angle here that is from this angle A. This is 90 degree. By theory, this incident wavefront, we already know that incident wavefront is perpendicular. The rays are perpendicular to the incident wavefront. So this angle will be 90 degree. Similarly, this angle will also be 90 degree. This angle and this angle will also be 90 degree. So if you look here within these triangles, both of these triangles, A dash, B is equal to B dash, which is equal to VT. Also, angle A dash, A is equal to angle B dash, which is equal to 90 degree. So, triangle BAA dash and this triangle, both are almost similar to each other. Now, see if BAA dash is similar to B dash A dash, means both these are similar. This triangle is similar. So what happens? It means these sides are equal. Both these angles are 90 degree. This is the common side. It means this angle will also be equal to this angle. So what did we prove? Angle of incidence is also equal to angle of reflection. And that is what is reflection basis of wave theory. It means incident, reflected ray all lie in the same plane. That is definitely there. But proving IR was difficult. No. So these are your laws of reflection. So both the laws of reflection are directly proved by this. Or laws of reflection are directly proved by our Heinz principle. Similarly, we'll prove refraction also. That refraction can also be proved through Heinz principle, wave theory. But if you have to prove wave theory on the basis of reflection, not your ray optics, then do as it is written on the screen. And it's better if you mention Heinz principle also somewhere in your answer sheets whenever questions are given. Noted down, reflection we'll do, then we'll move on to different topic. Let class, same thing. Now we have to prove refraction on the basis of Heinz principle. Heinz theory you can say, or wave theory you can say. Now again, incident wavefront will be there, incident ray will be there, normal will be there, same things. This is the incident wavefront. Incident ray will be perpendicular to it. This is incident ray. Incident ray will also be there at the different point. These are incident rays. So this is your angle of incidence. Here you will be having a normal. Normal is there. Here also you will be having a normal. This is what? This is angle of incidence. This is angle of incidence. Fine, angle of incidence is there. Now what will happen? See, for this point, this is one point, let's say B, this is one point, let's say this is A point. For A point, if you see and draw, here you will obtain a wavefront, secondary wavefront. This point will act as a source. Here you will obtain perpendicular to this incident ray. Right. Now your point is here. So for here, you will obtain the ray at, I think I have to erase this. You'll obtain it at this point because of this V point. See, this is, let's say, angle. These are two different medium. That's why this is N1, this is N2. Let's say this is rarer, this is medium 1, which is rarer. This is medium 2, which is denser. Fine. So here, if you will join the forward envelope, see here you're getting it like this. So this becomes your refracted wavefront and this becomes angle of refraction. This is refracted wavefront. This is angle of incidence. This is angle of refraction. Fine. Now see, this will be perpendicular to this. Here, no, why are we drawing it here? Because here diffraction is occurring. This was the incident ray. Here normal was there. So from this going into this medium, a refraction had occurred. Now same thing at this point also refraction will occur. Now again, secondary wavelets will be generated. Same thing will occur and this way it will keep on propagating. Wavefronts on the basis of the sources. This point and this point. See, here this is getting refracted, here this ray is getting refracted. Since this is at a very greater distance, so I had drawn it here. And this is at a very narrow, closer to this end. So that's why I've drawn it close on the basis of sources. Which ray? See, this is the incident ray. This is the refracted ray. There's a difference between ray and wavefront. There are two things here. In the last lesson, we only dealt with rays. Here you have wavefronts as well. This is the incident ray for which this is the refracted ray. Only the same case of refraction what we have studied in ray optics. Now, based on this incident, this is incident wavefront perpendicular to the incident ray. This is incident wavefront, and this is the secondary wavefront that has been drawn based on Heinz principle because of this source B. Similarly, this is incident ray. This is the refracted ray. Normal refraction occurred here. This was the incident wavefront. So this also became the new fresh source of incident wavefront. So similarly, here also secondary wavefront was generated. Now, when we join it, all the forward envelope of this gives us this secondary refracted wavefront. So this is refracted wavefront, not refracted ray. Did you understand the difference between rays and wavefront? Where are we using rays and where wavefront? How is ray from a forming? How is ray from a forming means? From A, not from A point. See, these were incident rays that were just incident on this mirror. See, this was a mirror and two rays. Simply, if this is a mirror, incident rays are incident like this. Fine. Don't look at this point right now. Focus on this only. Refraction occurred perpendicular to this incident ray. We had a wavefront. For this point, the wavelet was drawn like this. For this point, the wavelet was drawn a little closer because this point is closer. So wavefront will also be closer. This is far away. So wavefront will also be far away. If you join the forward envelope, you get it like this. Now understood? Okay. So these were the things that were required from here. So, but see, there are two different medium here, no? One is rarer, one is denser. So we'll not write V1T, VT everywhere. This is VT and this ray is also, this ray as VT. No, because medium is changing. So how can you write VT? Both the velocities are equal. If velocities are equal, then the refraction would have occurred. So this, let's say this is V1T, this is some V2T. So V1 is the speed of light in this medium 1, V2 is the speed of light in medium 2. And let's say N1 is the refractive index of medium 1 and N2 is the refractive index of medium 2. And let's also assume that V1 is greater than V2. This is greater than V2. That's why, no, at the same time, both the rays are reaching. So definitely first velocity will be greater. Now look at this triangle. Okay, let's name this also. No? Let's say this is A dash point, this is B dash. This point is B dash, this point is A dash. Again, look at the triangles carefully. This is a proof again. If you look at this triangle B, A dash, this above triangle. So if you write sine I from here, this is sine I, this is 90 degree. This is theta. So sine I will be what? It will be A dash divided by B A dash, right? Sine theta will be perpendicular upon hypotenuse. So A dash by B A dash. A dash is V1T. So we can say V1T by B A dash. If you look at this triangle B dash A dash, here this lower triangle if you see, and if you write sine R, so sine R will also be perpendicular upon base, that is V2T by the base B A dash. Now let's see. If we take the ratio, what will happen? So for the triangle, in triangle, first one was A dash. When you chose sine I, this was equal to A dash by B A dash, so which was equal to V1T by B A dash. Similarly, in triangle B dash A dash, sine R, when we wrote, this was equal to B dash by B A dash. This was equal to V2T by B A dash. Now, if you take the ratio between sine I and sine R, so V1T by B A dash into B A dash by B2T, just taking their ratios. Both will get cancelled, TT will get cancelled, we'll get V1 by V2. And V1 by V2, already we have discussed this, V1 by V2, N2 by N1, which can be written as V1 by V2. This is basically equal to the ratio of refractive indices. Therefore, you can say sine I by sine R is equal to n to 1. And this is what? This is your Snell's law. So if Snell's law is proven, it means refraction is occurring and you have proved the wavefront theory through, you have proven your refraction theory through the wave theory. So in the question, if any of these can come, reflection or refraction. Either refraction or reflection, be prepared. Most probably refraction can be asked. Most of the time refraction is asked in the exam. Yes, Sana. Any doubts from this part? You can note it. All of you can start noting it down. Okay, class. So this completes with Heinz principle. That was your first topic of wave optics. We have to start now. See, two topics are left: diffraction and interference. So I think let's start with interference only. Interference is a longer topic, and if you'll understand interference, diffraction will be completed within the class of next class only. So let's do one thing. Let's take a break now. Let's take a break of 5 to 6 minutes at least before starting with interference, so that at least you can get yourselves freshen up, scroll up through the pages. If you have any queries in this till here, if you have any doubts, let me know. After the break, I'll discuss it with you. Take a break, then we'll start with interference only. So all of you are here. 10 minutes break. I think this was sufficient. Can we start now? Khalid, Memuna. Okay. Salman, you there? Salman Sana?
Yeah, I'm here.
Okay. Let's start with interference. See, before starting with interference, so let us quickly revise the wave equation that will be used. Though we have discussed it. So wave equation, though we have discussed it, just let us revise it. If it is written y is equal to sine omega t minus kx, this we have already revised when we were doing from AC, we have been revising such equations. In EM waves also we had equations. Here y is telling you that this is displacement. A is the amplitude. Amplitude means the maximum value of displacement from the mean position. Maximum value of displacement is amplitude. Sine is your sine curve that is present, trigonometric function. Omega is angular frequency. T is time. K is angular wave number. X is position of wave. And this entire term, omega t minus kx, this is known as phase. That's fine. We write phase angle. Also, this angular wave position, this angular wave number k is equal to 2 pi by lambda. All this we have studied in EM waves. Just we are revising. So for electromagnetic waves also we had studied E is equal to E naught sine omega t minus kx. And the graph that electric field, magnetic field and propagation were all perpendicular to each other. Now see phase and phase difference. Phase and phase difference. See, if one equation is, let's say, A sine omega t. And let's say second equation of displacement is A sine omega t plus phi. So these are the phases. This is a phase. This entire term. This is also a phase. Phase means this angle. But phase difference means what is the phase difference between the two phases of the two displacement equations. Like if you write down the phase difference here. So here it will be omega t plus phi, let's say phi naught minus this omega t. So phase differences phi naught. And even without writing this was I have written it just like that. But if you see, only this term is extra, no? So this is the phase difference that is coming, right? So phase difference is phi naught. So always remember the symbol will be used phase difference. This will be phi naught in your equation. Like for example, because this will be used, y1 is A sine omega t plus pi by 4, pi by 2. Or let's take pi by 4, let's take it. In one equation, let's take it as pi by 4. And in the second equation, let's take it as A sine omega t plus pi by 2. And if you are asked to find out the phase difference, see, now you will subtract both of these. So phase difference it will be pi by 2 minus pi by 4 simply. Omega t will get cancelled anyways, right? So this becomes 4 pi minus 2 pi. That will become pi by 4 only, no? This will become, I think, 4 pi by 4 only. So this is the phase difference. Like this, we calculate the phase difference. So first quantity is phase difference. That is basic before we start with actual interference. First, tell me, phase difference and phase is clear to all of you? Clear or not? Okay. Salman is clear. Rest? Sana clear. Memuna Khalid, I hope fine by you both. Then you have path difference. This was phase and phase difference. Now, what is meant by path difference? Path difference will also be, see, these are the terms that are common to both interference and diffraction. And once these are terms, these will be frequent in our usage whenever we'll be writing and calculating it. Path difference means what? Let's say I have taken two slits. This is slit 1, this is slit 2. Slit means very, very fine cut. In a very thin sheet, I have made a very fine cut. Such kinds of drawings now will be very, very useful. Now see, here, let's say from source 1, this wave has gone. And from this second one, this is the wave, displacement wave that has passed. This is a wave. This is a wave. This is also a wave. Phase difference means what? Let's say this is P point. This is S1P. This is S2P. Phase difference is, path difference is the difference in both of these paths. So if I write that will simply be S2P means this path minus this path, S1P. Wherever you have doubt, please clear yourself. I think Sana remains only active in the class. She keeps on clarifying her doubt. If others also have, let me know. So this is how we write the path difference. Let's say with some symbol X, S2P minus X1P. Now, how will you relate this path difference? Path difference, I think normal also you can say, normally also you can understand by just the term. But you have to relate path difference and phase difference. So remember, phase difference divided by 2 pi is equal to path difference divided by wavelength. Please and please remember this. It means phi naught by 2 pi is equal to x by lambda. Do remember this equation, class. This is very, very basic equation for your interference, for your diffraction, for any part that you have to solve over here. Got it? This way you have to write. For example, if I say for some equation, phase difference is coming out to be pi by 2. If your phase difference is pi by 2 and you want to know what's the relation between displacement, that is path difference, and the wavelength. See, pi by 2, that is phase difference. This is phase difference. 2 pi is equal to x by lambda. This just gets cancelled. X becomes equal to lambda by 4. Such relations will be asked, will be used. Fine. Now see, before we move on to interference, what is actual phenomena? Few more small topics. When we were doing electrostatics, we had discussed a principle that was known as superposition principle. What was superposition principle, class? By now, I think it should be on your tips. Superposition principle. Yes, what was superposition principle?
The sum of all the forces.
Sum
Yes.
of all forces, like in a point. If it's going on a point, it's the sum of all forces, kind of.
Yes, added algebraically. That was the name. Good, both of you. Khalid and Memona. See, similarly, when we were doing in forces for, see, superposition principle is just not valid for force. It is valid for any physical quantity if there are multiple physical quantities. So for forces, we had seen if number of forces acted at a point. So net force was given by simply vector algebraic addition of it. Right, we vectorically added it first and then normal simple algebra we did. Here what we'll do, same thing. I'll keep on writing this statement and I'll explain you. If a number of waves traveling in space superimpose, it means there are more than a single wave present. So many waves are present in space, so many of these waves are present. At a single point, these waves are acting. Then how will you calculate the net displacement? This will be having its own displacement, this will be having its own displacement, it will be having its own displacement, and so on. So the displacement of the resultant wave is given by simply algebraically adding it. Y nth will be given by y1 plus y2 plus y3 up till y nth. This will be the net displacement for n number of waves. N means n number of waves. This is simply superposition principle. Also, you should be aware of coherent sources. Right now, no, I'll be using coherent sources, non-coherent sources before when we'll start with interference. So here also, let me tell you what are coherent sources. Before that, path difference, clear? Path difference is simply the difference between the two paths. You can do one more thing. The way now this Salman reacts, he simply sends up a thumbs up. So that's why he doesn't need to unmute himself or reply or type in the chat box. That's why also you can make things clear when I'm asking, if you are having difficulty to unmute. Otherwise, let me know if you have any queries, any doubts. So superposition principle, I hope it is clear till here. Any doubts you have, do let me know. Okay, good. Yes, I was telling about coherent sources. Yes. Coherent sources are very important. Then you can copy all these portions and still let me know if you have any queries, any part you have not understood. Let's say this is some source S1. At this screen, the source is emitting a wave. This is another source 2. This is also emitting a wave. Lambda is the wavelength of this wave and frequency is nu. Lambda is here is lambda of the wavelength and the frequency is nu. And the phase difference is pi. So listen, sources that emit light waves having same frequency, same wavelength, these are known, and with a constant phase difference. Both have a constant value phase difference. These are known as coherent sources. So coherent sources are what? These are sources emitting light waves of same frequencies. All right, both should have the same frequency, same wavelengths, and the last condition is and a constant phase difference. Among all the topics that we have discussed, this one is quite important from your understanding point of view. Also, it can be asked in the exam. Direct definitions asking is a little less chances there, but it can be asked. Now, two independent sources can never be coherent if their phase difference is variable. If the phase difference also becomes variable, rest of the things remains the same, then it becomes, they cannot be, they are non-coherent then. Non-coherent. Non-coherent sources. Fine. This is what is meant by a coherent sources. Now we'll start with interference. What is actual meaning of interference, definition of interference, everything. These were the basic terms common to both interference and diffraction. All right, note it down.
Excuse me, ma'am. Sources. What is that?
Emitting sources emitting light waves.
Yeah. Thank you.
Now see class coherent sources we have discussed. Coherent sources are sources which emit waves that have the same wavelength, same frequency, and a constant phase difference. Means if the phase difference between both the waves is 180 degree, it will keep on remaining 180 degree only. In such a way, they will propagate. Now the main part, interference. So interference, what the normal term interference has an English term. That is only to interfere somewhere. So superposition of two waves. If two waves are there, these are two waves, and these two waves are from two coherent sources, and somehow they superimpose each other. Fine, these two waves superimpose each other. So this phenomenon of superposition of waves from two coherent sources. This is important. Otherwise, calculation would have been very different and difficult. Coherent sources, this is known as interference. So interference is, this is just for our understanding. What the actual definition, the definition that you have to mention in your exam as well. It's the phenomenon of redistribution of light energy. How will the light energy will redistribute? We will see. Dark bands will form, light bands will form, fringes, which we'll call, will form. So basically, interference is what? It's the phenomenon of redistribution. Redistribution of light energy. Redistribution of light energy. Light energies will redistribute. It means the particles will arrange themselves. Why will they arrange themselves? They'll arrange themselves due to superposition. Due to superposition of light waves from two coherent sources. This is known as interference. Interference. Fine, this is known as interference. And you have a very, very major experiment for this, which is known as Young's double slit experiment. Anything that can come for sure is your Young's double slit experiment. Not only for class 12, for any entrance exam, if you appear, one question from YDSC is definitely there. This is very important, Young double slit experiment. Young's modulus, you must have heard of Young's modulus of elasticity. It was there last year. So this Young's double slit experiment is here. Single slit also exists, but double slit experiment is very important. What happened in double slit experiment? No. See, there were two slits. Fine. S1, S2. Both slits were separated from each other. Let's say this is small d, and this is a double slit. This is a double slit. So you will be having a source. Now source will do what? Source will produce waves. Fine. It will emit waves. Now these waves will pass through one slit. It will then pass through another slit like this. And a screen will also be kept. A screen will be kept. Now here what you will observe, at certain places, you will be able to see formation of very bright fringes like this. This is known as a bright fringe. Now, why is this happening? Because here, both the waves are having their same phase. So they are getting superimposed. So a very bright fringe is formed. Whereas it means both the crests are together. Here, both the troughs are together. Or you can see at some places, you will be able to observe formation of dark fringes. Yes, yes, same phase because they are emitted from a coherent source. Correct, Sana. So dark fringes means what? This is one wave. Now others trough is coinciding with the others crest. So plus with is coinciding with minus. Here plus with minus. So that's why you're getting dark fringes. This is the physics behind it. Why bright fringes and why dark fringes? But this is the phenomena what is occurring in Young's double slit experiment. This was what he did. Even you can perform Young's double slit experiment. Single slit also you can do. Usually this is done. Comb, no, you have comb. So what you can do, comb has very thin slits, very, very fine slits comb has. So what you can do, you can wrap up the comb, leaving any two slits, two threads of or pieces of comb we have. No, you can leave that. Then what will happen? When you leave that part, and then you put a laser light or any kind of light, same dark fringes and bright fringes you'll be able to observe. I think in some students who take investigatory projects in class 12, many of these perform Young's double slit experiment as well. So that can be performed by you also. Even if you cover the comb, fine two slits will be there. Why at the center we are getting bright fringe? If it's coherent, then how do we get dark fringe? See, same phases are there. Phase difference, wavelength is there, frequency is same. But a wave has a crest and a trough. This is actually known as constructive and destructive interference that we'll discuss also. This is actually a part of constructive and destructive interference. Having wavelength, having frequency is a different term. You can have frequency, you can have wavelength. That is a different term. Having a wave, trough, and a crest is different. See, in double slit experiment, coherent sources emitted the waves that give you phenomenon of interference. But superimposition can occur independently, no? Superposition of two waves. How the two waves will superimpose each other. That is entirely different. That is independent of wavelength and frequency. So how the superposition is occurring is giving you the type of fringes. These are basically energies or particles of waves that are accumulating. So all the waves where the particles accumulated, you obtained bright fringe, where the waves constructively interfered with each other, and where the waves destructively interfered with each other, you got dark fringes. Got it? So coherent sources are there, definitely. But this has superposition of waves is not depending upon what do you have, right? What the wave is final forming. Final formation of waves is because of the waves properties, phenomena of waves. That's why we are studying wave optics. This is the reason. Got it, Sana? All right, so we have to derive equations. Do one thing, note it till here, then we'll do equations. See, equation of waveforms. From both the slits, if you talk about slits S1 and S2, let's say Y1 is A sine omega t, and Y2 is having a phase difference that is phi, that is A sine omega t plus phi. Sine omega t plus phi. Now phase difference is what? Phase difference is this phi. All right. And also remember, intensity is always proportional to the directly proportional to amplitude. So we'll be using this formula. I is equal to Ka square everywhere. So similarly, intensity is also I1 will be equal to Ka square, I2 will be equal to Ka square. Now amplitudes are different, so I'll not write A here. Let me make it B. Because amplitudes are different. No? Frequencies and wavelengths were same. There wasn't anything about intensity. Now, when due to superposition, y will be equal to y1 plus y2. It means A sine omega t plus B sine. Let me make it here also. Please. This amplitude is A, this amplitude here is B. So this is B sine omega t plus phi. Just to differentiate, because both the wavelengths amplitude are different of these two waves. Now see, we just have to add it. Y is equal to, just a second. Now see, if you add both these waves, omega t plus sine plus theta, sine A plus B. So when you write it, this becomes, see, this remains A sine omega t. This is B. Now sine A plus B, this is written as sine A cos B plus cos A sine B. Now see, A sine omega t, I'm multiplying B with this term and then this term. So this becomes B into sine omega t cos phi plus B cos omega t sine phi. Do not write it right now. I'll give you time to note it. Now, if you take sine omega t common from here, so this becomes sine omega t common. Here you are left with A, and here you are left with B cos theta. See, sine omega t I have taken common. So from here A, from here B cos theta plus what is left? B cos omega t sine phi is left. So this equation is left from here. Now see, this term, no, A plus B cos phi. This is, let's say this is some R cos theta. R is the resultant amplitude. Fine, let's say, see, A plus B is the amplitude. Let's say R is the resultant amplitude. Resultant amplitude. Fine. And theta is the phase constant of the resultant. Phase constant of resultant wave. So now see, if I'm referring A plus B cos theta as R, this term I'm writing it as R for the time being. So Y will be equal to sine omega t. This term I'll write it as R plus B cos omega t. This is B cos omega t. Okay, one more thing. B sine phi. This is, I'm writing as B sine theta. So I'm writing this as sine omega t R cos omega t R sine theta. Let's take R common. So here it will be sine omega t cos theta. Okay, from here cos theta will also be left, no? Sine omega t A plus B cos theta. So A plus B cos theta, I'm writing it as R cos theta. So cos theta will also come. This is our cos theta, no? So this here cos theta will also. And this is our sine theta multiplied by this cos omega t. Now if I take r common, what is left? See from here, sine omega t cos theta is left, plus from here sine theta cos omega t is left. This is a derivation resultant you have to remember. Now see, equation of resultant wave, how to write? R. From here, if you take the average, this term, omega t cos theta, and from here, theta cos omega t. We are writing this as what? This equation of resultant wave is written as sine omega t plus theta. So this is the equation of the resultant wave, which you have to remember. For the derivation, you can look at the above part. This is the equation of resultant wave. All right, quickly copy it down. Text me done when you are done. I'll stop the class.
Ma'am, could you again explain the derivation, please? I didn't understand after
Okay.
the second step.
After which part? This part.
It's like after
R
the,
sine.
like how did you convert b sine omega t plus phi to sine omega t cos phi? That one, second line.
Okay. This part, last part. Okay, see here. A plus B cos theta, this is I'm referring to as R cos theta, and everywhere this will be referred to as R cos theta only. This is the resultant cosine. Similarly, B sine theta. From here also, no, B sine theta. This is written as R sine theta. And from here, A plus B cos theta is written. Now see. Here I have replaced R is what? R is amplitude of the resultant wave, and phi is theta. That theta is the phase constant of the resultant wave. All right, phase constant of resultant wave. Now when we substitute both these in this equation, in this main equation, this equation in this main equation, we get sine omega t R cos theta plus R sine theta cos omega t. Now, if we write R sine omega t cos theta plus R sine theta cos omega t, from here we can take R common. Now, when R, that is the resultant of the amplitudes, is taken common, we are left with sine omega t cos theta plus sine theta cos omega t, right? Till here it is left sine theta plus cos omega t. Now, from here, if we take the average of sine omega t cos theta plus sine theta cos omega t from here, and you compare it with the main equation that you have, main equation of the waves that we have, that we had initially discussed. Yes, this main equation, y is equal to a sine omega t minus kx. Then if you compare it with the main equation, then you're getting that this first term is representing you omega t, second term is representing you theta. So that's why we're saying this is the equation of the resultant wave. Sine omega t cos theta, if we take the average. From here, see, sine theta has been taken common, right? Sine omega t cos theta plus sine theta cos omega t. Equation of resultant wave is r sine omega t plus theta. This is from the main equation that we have studied. This is one of the equations. This is your answer. Your answer is stopped here also. This is the additional equation that we have studied. We are not converting all these equations. Still here you have received it. Now this is the main equation that we have studied, equation of the resultant wave. So I am saying more than this equation, no, r sine omega t cos theta plus sine theta cos omega t. This equation is equivalent to this. So it's instead of using this equation, the second last equation, you can directly use this equation as well. Understood, Khalid?
Yes, teacher. We don't have to
Okay.
learn the derivation, right?
No, you have to learn the derivation, because it can happen if it is asked to derive. Then you can keep it your answer till this step also. This derivation is not so very important. Resultant is usually not asked, usually intensity, and the resultant for the intensity is but just have a look. By chance it is asked in your exam, then write these steps only. Usually it is not asked in your exams. Fine. Usually those equations are asked to find out the resultant amplitude of the resultant wave. So that we'll see in the next class. Okay, so if it comes to write it that step, but mainly you have to use the final equation. All right, copy it quickly. Your time, I think, is already up. Quickly copy it down. Just text me done. And then as you all will keep on completing it, you can leave. Monday, you have test of ray optics, complete ray optics. Just a reminder. I hope it's fine, or do you want to reduce the syllabus or what? I hope it's fine, no? Let me know. Your view, if the syllabus is
Yes,
too much,
teacher,
then let me know.
fine.
Okay. So all those who have completed, you all can leave. Thank you so much.
Thank you, teacher. Allah Hafiz.